dear students. Welcome to Nuclear Physics 1 lecture number 13. I am Dr. Parvez Ahmad. In this lecture, we will have a discussions on the half-life of radioactive materials and mean life of radioactive materials. So let's proceed towards today's lecture. So first we will start from the half-life. We will have a formal definitions for the half-life. That is, the half-life is the time it takes for half the atom of a radioactive substance to decay. I mean, this is the formal definitions for the half-life of a radioactive substance. The half-life denoted by the English alphabet T with the subscript World War II. World War II means for the half, and T is for the time, so it's mean half-life. So what is the half-life? The half-life is the time it takes for half the atom of its substance. Substance means radioactive substance to decay, and that we will further clarify for from an example. So we have an example. We have 20,000 atom of a radioactive substance. So if the half-life is 1 hour, so how many atom of that substance would be left after? I mean, we are considering a formal example in order to clarify the example of the half-life. So for that, we consider a radioactive substance which has initially 20,000 atoms. So we consider the half-life as to be 1 hour. So we will try to find out that how many atoms will remain after 1 hour. That is the first half-life. So here you can see in this table we have the time on the left, and we have then we have number of atom remaining, and at the last we have a percentage of the atom remaining. So initially we have 20,000 of atom. So 1 hour uh, is the half life. So how many atom we will have? So after a half life of 1 hour, we will have 10,000 atoms remaining in the substance, and that will be 50% of uh, the total atoms. So what will happen after 2 hours? That is two lifetimes. So after two lifetimes, the number of the atoms remaining will be 5,000, and that will be equal to 55% of the total atom of the radioactive substance. So after 3 hours, that is three lifetimes, the total number of the atoms that we will left in the substance will be equal to 2,500, and that will be equal to 12.5% of the total amount, that is 20,000 atoms. If we consider, I mean, we can clarify further this concept from the graph here. So here you can see the shapes. This is the initial amounts of the substance that we have. We have that in circle, rectangular form, and triangular form. So this is the initial substance. So after first half life, the substance remain will look like this. I mean, here you can quantize or quantify the concept for yourself, and these are the substances which remain after two half life. uh, this is after three half life, and this is the quantities of the substances after fourth half life. So this is exactly I mean what is mean by the half life. So I mean, let's further classify the concept of the half-life, and we will try to derive a mathematical relations for the half-life. So for that, we can say we do some considerations, and that is if n naught nuclei are present at time t is equal to 0, and one half of that number, that is n is equal to n naught over 2, have survived after time t, so we can write the relations like this according to the law of radioactive decay. That is, n is equal to n naught exponential minus lambda t. N is the number of the nuclei that represents at time t is equal at any time t, and naught is the nuclei that represented time t is equal to 0. So this is the relation you are familiar with. So according to the conditions, just like given here, if n is equal to n naught by 2, so we just put this value here in this relations. So we get n naught over 2 is equal to n naught exponential minus lambda, and instead of t here we put the half life expression for the half life. So you just do the simplifications. I mean, it's n naught is cancelled with the n naught, and then you take the natural log on the both side. You just do the simplification according to your mathematical skills. So you get the relations lambda, that is the decay constants, time the half life, that is equal to natural log 2. You further classify that. I mean, we carry the lambda on the other side, so it will come in denominators. So half life, that we denoted by capital T with a half subscript. So that is equal to natural log 2 divided by lambda, and the value for the natural log 2 is equal to 0.693 divided by lambda. So this is the expressions for, I mean, the mathematical form, the mathematical formula for the half life of the radioactive substance. That is, the half life of the radioactive substance is equal to 0.693 divided by lambda. Lambda is called the decay constant, which we will define or discuss here. So what is mean by the decay constants? So for the decay constant, again, we have to consider situations, or you can also call an example. And that situations, let you have given same amounts, that is 1 kg of two radioactive materials with the half-lives of 10 hours and 50 hours respectively. I mean, we have two substances of radioactive material with the same quantity, that is 1 kg. And one of the material has half-life 10 hours, and the others that is 50 hours. So for first materials, after 10 hours, an amount of 500 gram remains, and for the second materials, after 50 hours, an amount of 500 gram will remain. So what it means, so you can easily clarify from this example, that is, in order to decay of same amount, the second material is taking longer. Why is taking longer? Uh, uh, because of its larger half life. So exactly these particular factors uh, as only dependent upon the half life of that material, because here the half life is 50 hours for the second material, so it's unlike for the first material that is equal to uh, 10 hour. So the main factors that is taking longer for the second material to decay, that is the half life. Therefore, if any material have longer half life, so it will decay slowly. I mean, that is the key concept, that if we have materials, or two material, one material has half life, I mean, half life less than the other material which has a larger half life. So the material with a smaller half life, it will decay faster than the materials with a larger half life. So this is the key concept, and this property of the material is defined as the decay constants that we denoted by lambda. What it mean? It mean that the decay constant depend upon the half life. So if the half life is smaller, so the material will decay faster. If the half life is larger, so the material will take longer time to decay. So this property is defined as the decay constants that we denoted by lambda, and it is linked mathematically linked with the half life by the relations. lambda is equal to 0.693 divided by the half life. So this is the expressions for the decay constants in terms of half life. Another terminology that is linked with the half life or with the radioactivity is the activity. So that we will clarify from equation number 3. I mean from radioactive decay law. From that relations, we can write lambda n is equal to lambda n naught exponential minus lambda t. So we can easily cancel lambda on one side with lambda on the other side. So we get n is equal to n naught exponential minus lambda t. And this is the relation for uh, uh, radioactive law. So here instead of n and n naught, we can simply put a in n naught, so we get the relations, we get this specific relations that we call equation number 4 here. So here a as a function of time is the activity at time t, n naught is the activity at time t is equal to 0. So this is what mean by the activity. We call that radioactivity or simply the activity, and that was that's this relation, that this is simply the radioactive decay law. We have just put lambda on the both side. So this is how we define the activity. So what is mean by mean lifetime? So again, if there are a non-radioactive nuclei at t is equal to 0, so the number that is that decay in some time interval dt is given by the relations minus dn is equal to lambda n dt, which is equal to lambda n naught exponential minus lambda t dt. So if we multiply this number by the lifetime t of these nuclei, then sum over all the possible lifetime from t is equal to 0 to t is equal to infinity. So we get and then then divide by the total number of the nuclei, we get the average or mean lifetime. So how we can write mathematically? Mathematically we can write the relation like this. The mean life we can write by tau, that is equal to, according to the definitions or the discussion we provided above, is equal to 1 over n naught, and integral is from 0 to infinity t absolute value of dn, which is equal to integrals 0 to infinity t lambda exponential minus lambda t dt, which is equal to lambda integral from 0 to infinity t exponential minus lambda t. Now you have to evaluate this integrals. So when you do the after being solving this expression under these conditions, so you get the value, you get the final value, and that is equal to 1 over lambda. So tau is equal to 1 over lambda. This is the basically the expressions for the mean lifetime. The unit, the SI unit of radioactivity is called becquerels, that we denoted by capital B with a small q, and 1 becquerels is equal to 1 decay per second. Another practical units for measuring radioactivity is called curie or curie, and 1 curie, that in short we denote by capital C, the small I, and that is equal to 3.7 and to 10 raised to the power 10 becquerel. That's all we have for this lecture. Thanks for watching. See you next lecture very soon. Stay tuned then, because in next lecture we will have discussions on problem on radioactive decay. We will discuss the problem relevant with the decay constants, activity, and mean lifetime. So stay tuned for the next lectures. Till then, bye bye.